Okay. Back to the old sinus coal mine. I got some ideas here. Okay, here's what I'm thinking, guys. Sean was cluing me into part of this last night too, but like, look. X here, what we're doing here is we're kind of just converting all of this. We're converting what quadrant you're in, or what octant you're in, into an integer down here, right? And then doing some stuff with it. All right, so we take the angle, we divide by pi over 4, or we divide by 16, or we floor it, we divide, whatever, right? All these things. But we know x is not negative because of this up here. We know x is positive, right? We know x is not negative. So taking the floor is the same as casting to int, casts round towards 0. But when you're always positive, that is the floor. So all this stuff where we dance around and float and doing weird stuff is not really that necessary. All right? So first of all, first we go to floor, then we divide by 16. That's a right shift by 4, okay? If this is an integer. And then we floor again, which doesn't make any sense, honestly. Well, okay. Like, this only makes sense if you're in float. If you're in int and you right shifted by 4, then that's automatically a floor because you shifted off the bits, right? And then we multiply by 16. That's the same as left shifting 4 if it's an integer, right? So instead of right shift, left shift, you could just mask off the low 4 bits, okay? And then we cast it to int anyway at the end. Right? But also, all this y minus is doing is like subtracting off high bits anyway. So the y minus is the last part that I'm confused about, right? This just wants a few bits out of the number. That's all it's doing. And it's doing a bunch of math to get it. All right. So we could simplify all this. Do you hear what the rock is cooking? Yeah, what's not clear to me is like which bits do we actually want, right? Um, so we take x divided by pi over 4, right? Okay, so this is our initial integer, is cast to int x divided by pi over 4, right? This could be a large integer if our input is large. That's the point, right? This is a sine function, which you would think, takes low angles, but it's supposed to handle anything, right? So we divide by pi over 4. We cast that to int. We mask off the bottom bits, okay? Wait, we're just taking the bottom bits. Masking off the bottom bits and subtracting that from the original number is just anding by the bottom bits, guys. My thesis is all of this goofy crap that we didn't think about last night because we just were working on the function. All of this goofy crap is we'll include this. J is, we'll put the cast S32 in here, but we probably don't even need that. So we cast to S64 x divided by pi over 4, all right? Let's just put some parentheses here. We're casting that to S64 and OX F, right? Are you following me on this? All of this code is just that. I think. And the S32 is not even really necessary, right? We don't need that. Oh, but we're using y as well. That's the issue. So we're going to say we're going to break this out. We're going to say iy for integer y. We're going to say iy is this. Y is cast float iy. This is, wait, why are we using y? See, we should just be able to use j, honestly. We're going to do this for now, but I think we could simplify this even more. Right? Okay. So we go to int, we go back to float, and we and the int version with f. Yeah, it's true. Okay, we could do this. You're right. We could do this the other way around. We could go y is x over pi over 4. Oh, no, because y has to be the floor. That's the point. And so we don't want it to call floor. So this cast to int is doing floor for us, and then we're converting back, right? Okay. See what happens. Whoops. Wrong window. So this was Sean showing me that a cast in LLVM just emits a thing. Although I don't know why it's allowed to, because I thought if this double is negative that this would go the wrong direction. So that's weird. I don't quite know why that's legal, but we'll accept that it is for now. I've got too many web browser windows open. Okay, undeclared identifier Z because we never made Z. This is weird code because it just keeps reusing variables. Like Z is like the general purpose work variable in here. All right, guys, you see how these numbers match? What does that mean? Does it mean that our code is wrong, or does it mean that our code is correct? I'm confused on this issue. Look how they match. All right. Rip all this. So let's just see what that did to the speed in the game. You spot one digit off. Yeah, there's one digit off. So the deal is we are comparing this against the reference implementation that's in libc, and they're not exactly the same. So there's one digit off. There's one digit off. This is fine. Least significant digit being off is fine. For our purposes today. All right, let's make a release build. And I hope I didn't leave something goofy in the game. And we can see we were at like 7.2 milliseconds in our little benchmark. But then, of course, my theory is we don't actually want y to be big. Except there's this weird stuff down here where we're see, like, this is so goofy. Like, it's using y for one thing, and then starting here, y is a totally different thing. It's like this code, it's minimizing the number of variable names, which is very confusing, right? So I don't like this use of y. This use of y kind of makes sense because, like, the sign function sort of returns y. I don't know. But, like, this shouldn't be called y. Should be a different variable. Okay. Oh my God, guys. That made us, that was like a 40% speed up. that was huge. Plus 40 DK fees. Yeah. That was major. Okay, so for people who have not tuned in before, what we're doing right now is once per frame in the middle of the game, because I wanted to have just the code compiled at the same optimization settings as the game is and all that, and it's just easy to draw the profiler and stuff. Um, Once per frame, we're doing 400,000 calls to sign, both from libc and from this sign that we're using, right? And we're just putting them in a global array so that this doesn't get optimized out. And yeah, so we can do 400,000 in about 4 milliseconds. And libc can do 400,000 in about 3 milliseconds, so 2.5. So we're getting there though. We're about 1.2 milliseconds slower than libc, which is still a lot, but less than yesterday. I'll just show you. Oh, it's not worth it, but it was like 7 point something milliseconds. All right. Bam. Actually, let me email Sean this because so Sean saying, keep in mind this breaks for doubles above 2 to the 64. So you can either fall back to a slower path there or just ignore it, since values about 2 to the 64 are effectively random anyway. I mean, that's a good point. Okay. It is a good point. So we are tremendously faster, but we are not currently handling the very valuable angles in the neighborhood of 2 to the 64. Which, okay. How many bits of accuracy, like if you were to go around a circle in the neighborhood of 2 to the 64 in a double precision floating point number, we could print this out, right? Just to see what happens. So you're stepping by 1024 at a time. In other words, you're not going around a circle at that point. You're just changing numbers. All right. So this is the weird thing where like we start making this into a different function than it originally was. I don't know if you saw the benchmark, but like, let's run it again. I'm just, because the number makes me so happy how much lower it is. Like, we were at 7.2 last night, 7.2 to 7.4 because I reverted all the stuff. We're at 3.6, I guess, about. So it's like half. It's half the time. By doing this. So we're still slower than libc, but we are no longer 3 times slower than libc. We're just like 50%. And this is just the first attempt. So like, there's still weird stuff that happens, right? So like, we use this big value of y down here. And we subtract it from x. And I'm like, and this is like modular arithmetic, but we're already doing modular stuff. Like the same way that this could collapse to this, I kind of feel like I just don't quite understand what this is doing. But if you didn't feed the big values down here, maybe you wouldn't need to do modular arithmetic. Like, okay. Anyway, okay. Let's actually comment this. So here we cast to S64, which will not preserve integers greater than 2 to the 64, or not preserve input angles greater than 2 to the 64, but we don't have enough precision up there to sensibly perform trig anyway. The original Cephes version of the code that did float stuff here was 2x slower than our new version. It does not seem worth a 2x slowdown to maintain output compatibility for numbers that are useful. I don't know what to say about that. To maintain academic those floors, that was me just temporarily uncommenting those so that I could email you. This is the actual code now, right? So let's verify that I did that correctly. Yeah. So, yeah. So all this is doing, people, is we're dividing by pi over 4. We could change that to a multiply, but I'm pretty sure the compiler is doing that, right? We're dividing by pi over 4, casting that to integer, which, by the way, x is positive, so that goes towards 0. Sean, in the example you emailed me, I don't understand. I thought casts were supposed to go toward negative infinity. And in the example you emailed me, there was no knowledge about the sign of the input double. So I don't know why it was allowed to do what it did. But maybe there's a rounding mode in that instruction or something. But yeah, I don't get why that code was allowed to do that for negative numbers. Anyway. Okay, so here's a weird one. This is kind of redundant with this. So like we're ANDing by F, and we're not ever using that bit, and then we're ANDing by 7, right? Now, that could make a difference here, but like maybe we only AND it here. You know what I mean? So I'm going to claim that this, right, is this, and then wait, right, yeah. I claim that we just need to do that, which is not tremendously faster, but like a little bit. Isn't j plus 1 basically the same as j and 1? What? No. Get rid of the and f. Oh, just do it at the end. Right, okay. No, that's a good point. Who knew this was going to be as fun as a Zachtronics game? Okay, it's a good point. Like, this and is not necessary because this, it doesn't affect this, right? And so we could just do the and down here. Okay. Also, I want to decide what to name these things. So you might not have been on here yet, Sean, but like I was noticing this code does a thing that a lot of this code seems to do where like it reuses variables for totally different purposes, and that gets confusing. So like this y here is something about which octant we're in, but then down here it just becomes the result. So I think I want to rename y down here. Like I want to say, like this y has nothing to do this y has, oh, we still have to optimize our sign variable, by the way. But this y has nothing to do with this result down here. So when we look at what we can do with it, we only have to look up to here, right? Why not do j equals y plus 1 and 7? Because you only want to add one. You only want to add one to bump it up to the next even number. I don't understand what map zeros to origin means, honestly. So I don't know why this. And also this is really scary if this number is big, right? So we kind of would just rather, like, this wraps around a circle. So like, I think we can make y be small by casting j instead of iy, right? But let's not worry about it yet. Let's fix this thing. So here, let's just do this and make sure it works. So j is iy, all right? And then we do the and later, right? All right, that all still works. So this doesn't need to be j. I'm going to call this like IY. Maybe that's less clear because I see y's all over the place. Let's call this j for some reason. Okay? All right. So j is the integer. Now, what I'm saying is this cast, oh no, because it has to be, before the plus equals 1. Or, wait, what? No, this plus equals 1.0. Okay, wait. If we move this down, then we get rid of this. And then y is known to be small. And now j plus equals j and 1. That is true. Let me just try this. I don't want to get too far off my horse here. Okay, we have a problem. Wait, did we have a problem before? Maybe I didn't notice. A lot of these numbers are the same, but then it gets weird. Oh, the reason, okay, I can't do this. I can maybe do this. The reason I can't do this possibly yet is because we use the value of x relative to y down here. So if y shrinks, if y gets rounded and x doesn't get rounded, that's bad. So, all right, we fixed our problem. These numbers are the same. So as Sean suggests now, instead of this, j plus equals j and 1. All right. This is fun. And honestly, this doesn't have to be 7, right? Because there's no 1 bit, right? So we could put 6. Just to be funny. You're saying the third bit is used for the sign just below? No. J can't actually be 3 here. We made sure it was even up here. I don't know what map zeros to origin means. That must be with the polynomial that we're talking about or something. I don't know, right? Anyway. See that? We use numbers every day. Does that being 6 actually matter? It doesn't matter for performance, but I think it makes the code a little more clear. Because you know, J is actually now, it's only 2 bits. It can only, there's only 4 things it can be. And then this is almost just masking off the top bit, right? Like j greater than 3 minus equals 4 just means mask off the top bit. But we also have to do this. But, okay, let's start playing with this now. Because maybe we can get rid of this if, right? Because if we just say the top bit goes into sine or gets x, you know what I mean? I think we can do this branch free. I think that's a thing. But we want to make sine a different thing than it is. Hold on, let me get some water. Think map 0 to origin is maybe change j so that the result of the remainder is going to be minus pi over 4 to pi over 4. My brain is not absorbing this. Yeah, let's see if we got any faster. Wow, my tea's cold already. Tragic. How have we been live 40 minutes already? How is that? I feel like we just started. Is that broken? We did get faster a little bit. Oh, maybe not really. I don't know. When it's this noisy, it's hard to tell, honestly. A hair faster, I would say. Because before we were like 3.6 and then going above, and now we're like 3.57 and going above, you know. Is floor still ellipses? We're not calling floor now. We got rid of floor. Is there a construct that mimics the context manager feature in Python? I have no idea what that is. So, not intentionally. Okay. I forget what we were doing there. Okay. So instead of having this be a sign, which is 1 or minus 1, let's say negate, right? And it's going to be 0. But we'll set it to 1 if we need to negate things, right? So instead of this, we can do twiddle equals 1, right? And that already looks like something we can combine with this, right? Twiddle equals 1. Which really, oh, sorry, it's not called sign, it's called negate. This will also clear the confusion of saying sign and sign. All right. That's that. So, and then this if statement here, this is the last twiddle on negate. So we could actually, if we wanted to introduce another static if down here, we can get rid of this. Because we just say for cosine, this is one way, and for sine, it's the other way, right? But hopefully that gets optimized out. I don't know. That seems like a not hard thing to optimize. Oh, except it's not, because this isn't a Boolean. Like, the compiler doesn't know. All right. The value of k. I've got a comment. Yeah. I don't even remember what that was all about. Whatever. I'll write a better comment later. Okay. So what I'm thinking is, oh. Right. Like at this point, j is 0 or 2. So we can get rid of this if statement. Okay. All right, hold on. One at a time. Let's make sure we didn't break it. Attempt to use... Wait, what? Why do you think that's a... Oh. I didn't do this operator, guys. Because I thought... Like, I was trying to streamline things. And I was like... Nobody's ever going to want that. You know what? Oh, wait. Wait. Oh, it's XOR. It's not twiddle. Guys, it's this. And I don't know if I did that operator, I mean. Okay. Why is that so confusing anyway? Why was that way? Why was that way? You know what I'm saying? All right. You thought it was a syntax change? No, it's just me. Like, so Sean lives in a world where you do these kind of things all the time, and I don't. And so I just kind of forget. All right. It looks like we didn't break it. So, I mean, what do I do about this? Like, should I just delete this at this point? I think so. Like, Okay. So, if j is greater than 3, then j and 4, and furthermore, no higher bits are set on j. So the problem that I have right now is j is like frickin' 64 bits. I'm just gonna make this 64 bits. It annoys me that it's so much bigger. Like, we only need 1 bit and it's 64 bits. But like, anyway, hold on. If j is greater than 3, then j and 4, and furthermore, no higher bits are set on j. So if we want to toggle negate, we XOR it with J right shift 2. J minus equals 4 is the same as masking J and 2. Okay, this is weird. This is going to be weird now because we're going to AND it by 6. We're going to use that bit and then AND it by 2, right? So like J equals J and 2, but we're going to go negate XOR equals J right shift 2. Yeah? Sounds right. So we got rid of an if statement. We are now, okay, some of this is just making the code more clear. This is making the code more cryptic. So I'd better explain it. But we wanted to get rid of the if statement for performance because the branch predictor might have problems with it in many use cases. Okay. Something like that. We're explaining what we're doing. Does that make sense to everyone? Check if the unrolled code is actually faster. That's true. Except I deleted what it was. Except we know what it was. Okay, let's make sure this works. We're gonna time this, and then we're gonna bring this back. Right. I believe the 5 was in the third slot. Okay. You agree that it seems like the AND 6 is redundant? Yeah, except we would need an extra AND to pick out that bit. Because the reason this works is because the high bits are 0. Unless, okay, we could get really crazy and say negate is allowed to have garbage bits in the high bits, and we only care about the low bit, but then we would have to mask it down here anyway. And at that point, like, who cares, right? We're not saving anything. So it's not clear to me yet how to get rid of that. And honestly, as things go, I'd rather work on removing a branch than work on removing an AND with a small constant, but yeah. Could store it as a bool that's either 0 or 4. Right, and then we can twiddle the higher bit. That is some Zachtronics thinking. Okay. We did get a bit faster again, right? We were like 357 before. Now we're like 347. Of course, everybody, by the way, I do not want anyone to be confused into thinking that I think that what we're doing right now is scientific, objective profiling that is reasonable. Not true. Like, I'm running this on a computer that's streaming and running a game and doing all kinds of weird stuff, and I'm eyeballing a rapidly changing number drawn in pixels on the screen. None of this is how you should really profile if you super care a lot, especially if you're profiling for small improvements. But we're not really profiling for small improvements right now. What I want to see is us to get way down close to the libc number. And when you do that, it's not really questionable about whether you got faster or not, right? Like, so, streaming and whatever should affect the libc number about the same as it affects our number, right? Anyway, this is not serious profiling. All right, just so we're clear, because there are people in here sometimes. There's 400 viewers. Some of these people are newer at programming, and I don't want to teach them that this is responsible. Why is my phone ringing? It's not even my phone. It's my iPad, which is not set to silent, even though my phone is always on silent. And Apple helpfully makes my iPad ring when I get a spam call on my phone. Thank you, Apple. Would you want to read the code that breaks well-established patterns like this? Well, it depends on how much faster it is. And like I said, I said what it actually is. All right. It's true. We can make it be bit 4 of negate. This almost, though, like we might lose an optimization here, because you could almost imagine a compiler realizing, oh, it's negative, so we can use the carry bit to assign. I don't know. That's probably doesn't matter. Okay. On a real world, should the compiler try to remove branches in this condition? Yeah, but this is the kind of thing, we're doing weird stuff that the compiler is not going to figure out or try to do. Switch it to and 7 so people would know that you just want to clear 3 LSBs. Well, but it's self-documenting. See, we had to figure out yesterday, right, that like, oh yeah, it becomes even and then things don't change it. So this kind of tells you, these are the possible values of this number. It's only 2 bits, right? That to me feels more self-documenting. That's why. But, it could be and 7. Yeah. You strongly disagree? Okay, well, that's fine. I don't feel super strongly about it either way. You could just say and 7 and then say, but the low bit can't be set anyway. You like Python for this kind of thing. Well, you can put OB111. We can do that. What kind of programming language do you think this is? Whoops. The one where I compile the wrong thing. You could do that. You don't need to use a programming language that's like 5 orders of magnitude slower than it should be in order to do OB111. Since we had a strong objection from chat, we'll do it this way. Like, oh my God. Why would you want to pay 99% of the performance of your computer in order to say OB111? It doesn't make any sense. Okay. Yeah, let's get rid of this if statement here. Remember, this if statement, this is a static if. This doesn't cost us anything at runtime. This one does. Oh no, we were gonna try this. Okay. So hold on. Let's remind ourselves what the numbers were. It was like 3, 5, 3, 4. 3, 4 and below with occasional spikes of weather. Occasional large spikes. Like, yeah, this is, this is computers, guys. All right, that's what it looks like though. So what we had said before was we thought that these versions of these functions should have been better. Wait. Oh, we have to bring these back. All right. So we'll see what that looks like. How are we an hour in? I just commented that how are we 41 minutes in and time is going really fast and now it's an hour in. At least I'm having fun. Six is OB110. Yeah, I know. See? Here, OB110. The final sign fix-up takes a probably unpredictable branch. The final sign fix-up. This one. I mean, it's a floating point number. So we could just twiddle the sign bit if we thought that was faster than a branch. What middleware are we using for sounds in FX? Unfortunately, we're using WWise to play sounds. Normally, I like to play sounds myself, have our own engine do it. Okay, it's way faster now. So that was a fluke that those functions weren't faster. You know what it might have been? So the thing is now we're doing way less floating point stuff up here, right? So maybe we were just hammering the CPU with too much floating point. And now there's less. There's still a bunch because there's this and then that function. But maybe it was just over the top before. And it wasn't able to compute some important dependency in time, right? But now that we're all integer up here, it's better. I don't know. That's just me talking out my speculation hole. It's a lot faster. Slower, but doesn't seem to spike. Yeah, I mean that is true, but that spiking, I'm not sure. I wouldn't expect this to exhibit spiky performance if it weren't in a noisy environment. Because this code runs a very consistent number of operations, right? So let's show what those are for people who weren't on last night's stream. These functions are just this, all right? So like, they're doing some multiplies and some adds. They're doing the same number every time. I don't know why it's more spiky. That is a good point. It did seem more spiky yesterday, and it seems more spiky today, but I kind of don't believe that that's anything too meaningful. Surely we're past using a bunch of Taylor series. This is a polynomial approximation. It's a 13th degree polynomial, the comment said. So, yeah. Okay. Still planning on working on compiler bugs today? Probably. I just wanted to finish this up a little bit because it bothered me that we didn't get a good speed up last night. Today we got a great speed up, so we're already winning. This is very, very winningness. All right, so let's say we did this. Negate flag. Okay. So we're going to do that. And then down here, okay, we have a problem actually. Because this relied on us masking off the lower bit. Right? If we just XOR here, we add a bit, and then we have to mask it off again later. And, oh, but we get rid of the branch. Oh, right. Wait. Yeah, never mind. This. So we have to update the comment above here. So we mask, right, the point is this is in the same position, right? Now, then this is redundant, honestly, guys, because look, this is just undoing what we did here if it's cosine. Am I actually doing the 0 or 4 thing? Yes, I am, Sean. This is where we're at. Because we can... Like, look, this is actually going to get us somewhere. We may actually be able to undo it. Because, look, if J negate whatever is just doing this again... We're double negating if it's cosine. Now, we're not profiling cosine, but, you know, that's bull crap right there, isn't it? It's really interesting how you manipulate these functions and you start to see stuff like this where you're like, wait, what? That was there the whole time. He's calling from inside the house the whole time. Maybe I'm confused. Okay. I mean, I think that's it, right? How bad did I break it? Not bad at all. Oh, wait. Yes, it did. Oh, God. Oh, God. Okay. What did I do? What did I do? Okay, hold on. Back up the bus. Back up the bus. All right. It's not redundant. It's testing a different bit. Okay, hold on. Let's think this through again. Or me needs to think it through again. Okay. So this is this, right? Okay. So, okay, got it. So this is actually, I did the wrong thing. So this is actually this. This is pretty weird, honestly. Anyway. Yeah. So the savings from not shifting earlier spends the shift here. Right. Okay, so this isn't right. This isn't redundant, first of all. Let's be clear. When I said that, that was wrong. It's a different bit. We may be able to take advantage of that in some other way, but it's not self-canceling. So that was an incorrect observation. Let's just make sure that this runs correctly. But yeah, like now we did make sine faster because we only shift for cosine now. But is that worth it? Is it worth saving one fixed shift in sine? Not necessarily, because there might be bigger ways. There might be better fruit to go after. For cosine, yeah, we might be able to combine these into different expressions for sine and cosine, right? So for sine, it's just this. For cosine, it's semi-redundant with and 6 above. Yeah. I mean, I don't know. I don't know, man. Why don't we just have a computer instruction that says just do all the things, do all the bit things in the right way in one cycle? Do all the things. Like, look, it's not that hard what we're trying to do here. Okay, so I'm kind of thinking that we undo the negate flag thing for now, just because it doesn't save us much. You meant to change it back to 7. Yeah, but it's not. It doesn't feel like it warrants a comment if we're masking with 7. If anything, the comment. Well, no, it doesn't need a comment now. You'd leave it as 0 or 1. Yeah, it doesn't. It doesn't seem worth it. So even though this is, in theory, faster, got to undo my wrong one before. Okay. Even though this is in theory slightly faster for sine, it's not really going to be measurably faster, and it makes the code more convoluted, and that makes it harder to continue to optimize because it's harder to think about and whatever, right? Like something that's 0 or 1 is something you can play with pretty easily. I don't know. I don't know. Like, saving one integer operation like that can be a good optimization in some cases, but not when you're doing the amount of math that we're doing here. It just doesn't make sense. We want to get rid of the branches, right? But we can do that. So I never got rid of this one, did I? Or did I? And did I accidentally undo it? So this is J XOR equals, or no, sorry, negate XOR equals J right shift 1. Did we not do that? Maybe we were just trying to avoid the shift, and then we ended up with a shift down here anyway. So this is just saying, so if J then it has to be 2. The only possibilities are 2 or 0 at this point, and so you right shift it by 1 and you toggle the bit. All right. Great. Let's see what our perf is now. You think the results were different this time at the last digit? We do have last digit differences. That's fine. We are not comparing here against our own reference implementation. We're comparing here against the libc implementation, which is a little bit different in terms of the results it returns. The kind of things we're messing with would not create least significant digit differences. They would create the result is the wrong sign all of a sudden. And that did happen a couple times when we messed up. You need only a quarter of a circle. Yeah. All right. I mean, it's about the same. Oh, this if that we got rid of was only for cosine. So we're not benchmarking cosine, so we wouldn't see any benefit from this in our current benchmark. It's just we more got rid of the if to feel good about it. Branchless sign fix-up is possible for sure, right? Yeah. Yep. I mean, let's do that. Okay. Do we already have one of these? Yeah. So we're going to go whoops, equals R Flint dot U64 XOR equals negate left shift 63, and then return Flint dot float 64. Is the optimizer going to do the right thing with that? Maybe. I don't know, man. That's really something that we haven't looked at. All right. Oh, it's U64 versus S. Oh, God. Let's just do this for now. I don't think that should change anything. All right. So, great. Let's see if that helped us getting rid of that if. It does in the C version you linked. Yeah, it's just like, I don't know what you have to tell LLVM about your language semantics in order to get it to do various things, right? Like, I feel like this shouldn't be a problem, but I don't know. I don't know. It's slower by a hair, or no, I don't know, guys. It does seem slower. I don't know why we're spiking more as well. Like what's going on with that? Maybe the computer's getting hot. It might not be. It might be the same. It's not a noticeable improvement, which is weird because I would expect that branch to be taken 50% of the time. Although it is, if you're moving around a circle, like we're not picking totally random angles. So if you're moving around a circle, it's maybe more coherent because you're in one quadrant for a while and then you're in another quadrant and so forth. Yeah. And so that's the thing is like maybe for a different use case, like if you're doing a particle system and you're calling cosine a lot or sine a lot, then um, on like random, like you're initializing particles to random angles that are uncorrelated with each other, then this might predict more poorly. I'm kind of out of ideas of what to do here. I think maybe I just want to comment these and then leave it. Now, when I say that it is not necessarily the responsible adult engineer thing to do to profile the way that I am profiling, it is also not necessarily the responsible adult thing to do for breakfast to eat a bag of cinnamon sugar pita chips. But that is what is happening. I am not attempting to be a role model right now. This is just what I wanted. Because we did do a good job. We got a good performance boost so far. Way better than last night. Would passing integers to the polynomial evals rather than floats do anything? I mean, that would wreck our function. So here's what I think with regard to working on this in the future. This is fishy to me, right? The only reason y has to be big is because x is big, right? If y didn't have to be big, we could actually do it after the mask, right? The reason y has to be big is this. But if instead we somehow brought x down at the same time, like what if we just f modded x by pi over 4? Like magically for free. I don't know. The whole thing is, how do you implement fmod efficiently? Yeah. Is there any well-known machine instruction way of doing fmod fast? I guess these parentheses are here for pedantic floating point precision mode, I guess. So you care a lot about rounding there. What do we think this is doing? We're just subtracting y times dp1 plus dp2 plus dp3. Like, this by itself is obviously faster if you don't care about precision, right? You would just say x minus y times constant. It's x minus y times pi over 4. I mean, that makes sense, but why is it being done like this? The comment extended precision modular arithmetic is not enough of a comment to inform me. No, the thing that makes people say UB can do anything is that the compiler can decide to delete the body of an if or a loop or whatever if it thinks the condition is UB, and then your code won't do that, right? I mean, that's the really scary thing. Like, to me, the right way to define it, if you're defining the language, is to say, if you read an uninitialized value, that's not UB, it's you're getting, it is defined behavior that you are getting an unpredictable number in the value, right? Like you need to scope what you're saying is undefined down to the minimal thing. And people don't want to do that. Like compiler people don't want to do that because they think they can optimize more otherwise, and that's just the wrong choice. See, we're just explaining. We're just explaining. Are we done here on this function? Or do we have something else to do? I am a lot happier with it than I was at a certain point yesterday. Right? When we first typed this in, we were 3 times slower than libc. Now we are 30% slower than libc or something like that. Which is not awesome, but not where we were, and that's good. I do feel like the trick to making this a lot faster is, like Sean said, we're basically doing fmod. So like sort of re-envisioning from first principles, like what do we know about fmod? And can we just like fmod x without doing all this stuff? In a reasonably fast way. Because like we made this way faster than what it was, but it's still like, still some stuff. This is weird. Let's try something here. We're being goofball. Oh, let's look at the perf again one last time. Make sure we didn't tweak it. I think fmod is hard and slow. The trick to making it fast may be a totally different algorithm. Yeah, maybe. Yeah, so we're 1 millisecond slower in this test, which is, well, we're like 40-something% slower, right? So libc is 2.4 milliseconds. We are 3.4. Not awesome, but much better than where we were. Okay. Yeah, the trick to making it fast may be a totally different algorithm where you don't care about range reduction in the same way, I guess, right? It's hard to imagine what that would be, though. You know, a useful thing to do, because we have these compile time parameters and all this, right? We could have a parameter to sine or cosine that says, I already know this is in 0 to 2 pi, or, you know, whatever, right? Because often if you generate an angle, you know that. Like often in your gameplay code, you don't want your angle to be like 20 trillion anyway, right? And so all the stuff making this slow, or a large amount of it, the range reduction thing, is maybe not that necessary, right? So I would be interested in figuring out, okay, look, if we know it's in 0 to 2 pi, what of this do we not need, right? Do we not need this? I don't know what that's doing. Do we not need some of this? And then you could put the range reduction in like a preamble that is only optionally compiled in, right? And a lot of people would be loath to do that because it's like, oh, it's another API call and blah, blah, blah. But in this language, it doesn't have to be another API call, right? You just have a third parameter. And, you know, sine and cosine up here, it would be a second parameter to these guys that just says, are we known to be in 0 to 2 pi? And then in debug build, you could even assert on that in these functions, right? That sounds to me like the year 2022 sine or cosine. You could change the extended precision remainder to something simpler and check performance. What is the extended precision remainder? Did we look at the disassembly for the libc version? We didn't. We did not do that. The thing that may or may not tell us very much. If it's a different algorithm, looking at the disassembly isn't going to tell us much. Unless they're doing the same range reduction with a different backend. Oh yeah, this thing. Let's say I mean, like what if we do that, right? How bad is that? It's pretty bad sometimes. It's really bad. But if we just care about performance, got to at least do x minus k1 times y. Then I'm not really sure what the point is here, right? Because we're only saving 2 multiply adds, and we do like a trillion more down, right? We do like, well, let's just see what the perf is here. If the perf isn't big here, it's definitely not going to be big from adding another term, right? Wow, what? Excuse me? Baking powder? How is that so much faster? I'm confused, guys. Because, like, look, this is a few multiply adds that we got rid of. But, like, we're doing, like, 1, 2, not a trillion, but, like, a few. I mean, okay, well, look. This is just x minus y times this, right? And that should get constant folded. The speed up is bogus. Oh, because the compiler is discarding all the y computation. And this, honestly, I don't think that we compile in pedantic floating point mode. So this thing that I just did, probably is what's happening already. Maybe not. Right. So if it throws away the y computation, that's this part. Well, it's literally just that. We don't use y anymore. So I don't... Okay. This is ill-advised. I don't think it would be faster, but because we know J is... God! I have to turn off my iPad, guys. Dear Apple, I'm trying to work. Don't let the spam callers bother me. A funny thought is because we know J is... oh no, J is not small. Never mind. I was going to say if we knew it was a small integer, we could just construct the float instead of doing cast the float, but that's not going to be... It's just going to be dp1. Right, because the... Well, I don't think it's just going to be dp1 because these aren't that far from each other. So like this will contribute a little bit. And so, I mean, they're doubles, right? So these will all contribute. It's just you won't get a lot of these bits. I mean, it is substantially faster. That is a lot. Okay, well, okay, so that gives us information though. The information that we got is, look, now that the branches are all gone, it's math. Math is our problem now. So I feel like, okay, we do have bigger errors now in the bottom. See this? So we're getting the right answer. It's just with more error. But it's like more than 10% faster. But Visual Studio doesn't need to take that much error to get faster. See Fmod with fast math. I don't remember what this F nasty. It's nastily storing a single word, status word. Oh, this is x87? We're checking the status word for what? What is FP? Computes the remainder. So this is a very straightforward fmod. This is not doing anything tricky. This is the fmod you would have had in 1995. Except for the move SS. Like what? Okay. This is just to return the value because I guess the calling convention is that the float return value is returned in XMM0. So yeah, this is not a very good fmod, if we're being honest. Um, I just don't remember how many cycles these instructions take. You sent your double precision floating point parser. I mean, what? I don't see a README on there that discusses. Oh, it's in the file. No? No, there's a copyright. I mean, this is totally off topic of what we're doing, but I don't see anything that explains what the properties are of the algorithm. Is there a file somewhere that says? Oh, wait. That's just the mul. It's a 64-bit multiple. I mean, so this is a limited precision parsing algorithm as well, right? So this will incorrectly round at some point. Or maybe it doesn't. Maybe it's got big nums somewhere. FP rem is 31 cycles on Coffee Lake. You can do a lot in 31 cycles. Yeah. Yeah, I mean, when you write an algorithm like that, you've got to explain to people what it does more specifically than, hey, it parses floats, right? Because, like, okay, well, this is a known problem where, like we were talking about the other day on the stream with Sean, doing the full answer is very painful. So if you choose not to do the full answer, which is a legit trade-off, you just have to explain what trade-off you made if you ever want anyone else to use it, right? You just have to say, like, look, we're not doing the full thing, but here's what we're doing instead, and here's how good the thing is that we do, like here's how much error there is, and whatever. 27 on Knight's Landing. I mean, so we were saying the other day, though, so floating point multiply was like latency 5, wasn't it, on most of these? Latency 4 on AMD. So, you know, that's only 6 multiplies. which actually is not good, but is not completely crazy. Well, it's six. Okay, it's six serialized multiplies. Okay, that is pretty bad. That is pretty bad. Okay. Well, I mean, I guess we're at this point where it's like, look, maybe this algorithm that is being used here is not actually the best one, right? Maybe it does a little more math than it needs to, etc. This algorithm goes back to at least 1993 because somebody posted yesterday. Sun Microsystems. 1993 was still, maybe that was Solaris. Maybe it wasn't Sunos anymore. But the point being, it's a long time ago. I was still in college at the tail end, or maybe that was my year off. So people may have better ideas about how to do this faster now. And I think that that is the right place to push on, right? Because we've got to the point where, like, look, we're just doing math. We're doing too much math. We worked on this code a bunch to make it faster than base Cephes, and we did by a good chunk. By more than 2x speed up. However, now we are in a place where we are still slower than the libc, than the Microsoft, the Windows libc version. And it looks like the bottleneck now is just how much math we are doing. So maybe it would be fruitful to look at a different algorithm at this point for something that approximates with fewer multiply adds in some way. Alternatively, it seems we are still spending a fair chunk of CPU power just to do an fmod on X, essentially. So if we had a faster way of doing that, we would be pretty good. Note that even though we have this variable j that is limited to a small positive number, for the math shown here, y has to be big, has to stay big, because x is big. That seems like an opportunity to fix something. Is it June 30th already? That's what happens when I just sit here and program forever. Small f's. Yeah. Sorry. okay. You know, we did some good things. We got the perf up. We did this good application of folding the code together. Um, I still don't know about this, about having the big constant versus a small constant. Who knows? Like not having the shift, it maybe doesn't matter that much. We could try that real fast, but I don't know. Okay, wait. Didn't we do the branch? Oh no, this x is float here. We could do branch free on this if we wanted to. You know, I forgot about this lost th thing, right? Which, by the way, means we don't have to worry about this 64-bit thing here, right? This is only a million or something. Wait. A billion. It's only a billion. So if you pass an angle bigger than a billion into this, it fails anyway. Sean says do it. So we can modify this comment, but this algorithm already bailed out. Well, let's leave this. And this algorithm already bailed out if the input angle is higher than losses, which is only about 1 billion, way less than 2 to the 64. Making things branchless is going to be better for other cases, but probably doesn't matter for this test case. Yeah, we could modify the test case really fast, right? To be like random angles. That's easy. We can go here and go like, right? I mean, then we've got a random function in the mix, but it's the same for both of them. Or we could store the angles. Here's what we'll do. Okay, so like this. Okay. So we do that. And then here we just say, let's do this, we'll do this, we'll do this, do this. All right. We'll do this. How does that sound? Randomize minus tau to 2 times tau. Because we do want to test the range reduction, right? I mean, let's go minus 4 times tau to 4 times, I don't know. Who knows? But I'm just reassuring myself. This doesn't run that code that we just typed. I just wanted to double check before we actually go do a thing. We have, okay. Call init random. Well, this is, so we start with a kind of a reasonable seed. Oh, but we should make sure, yeah, okay. So, yeah. What's a good number that's relatively prime with OX7FFFFFFF? How about that's relatively prime. Oh, I wrote it, but I never. No, I do. I call it right here. I was just too fast for you, Sean. Okay. Where are we at? Oh, interestingly, libc sign is a lot slower now. And so are we. But we're slower by less than libc sign is slower. So libc sign was at 2.4. We were at 3.4. All right. We went up to 4.4. libc sign went up to 3.8. So that's like 1.4 more louder. Maybe slower overall due to table lookups. That is true. Some of this might be reading the values out of the array, but I kind of feel like not really, not that much. It's going to be fully in cache, right? Oh, well, here's the question. Is one of these taking the hit of putting this in cache, right? So let's do this. In stupid, we're starting to be more like adult profiling people. Make sure the numbers are in cache before we profile. So we're going to say this. We're just going to read them and write them, okay? And then when these guys go read them and write them, it should be okay. I mean, well, they're pretty big arrays, though. They're 400,000. Should we do like multiple iterations over shorter arrays? That's 3 megabytes. But then they're both can swap order of sign and sign libc. $32K to $64K entries. Computers are fast. Yeah. Let's do this thing that people are suggesting. So if toggled else, I mean, I'm a little worried about what this is going to do, but we'll see. Right? I mean, or we could do them just both in a row every frame, right? I don't know. I don't know, guys. I am not Linus Tech Tips. Thankfully. I feel like both are writing the same table, constantly overriding each other. Yes. We are not wanting to save those values. We are writing the values so that the compiler doesn't say, oh, there are no side effects to this function. Let me just get rid of it. All right. Okay. Wow. Is it possible that we were over punishing ourselves by going first the whole time? It sure looks that way. Because this is what it was before, and now we're just a lot closer. Right? Let's do that just for giggles. Like, let's take out the caching again, or the prefetch. Take this out, and just do this. Remember what I said about this wasn't scientific profiling? This is an example of how you get bit when you don't profile very carefully. I mean, 0.2 milliseconds is a lot, man. Okay. So we are slower by like 0.65 around. But that's with all the cards maybe a little bit unfairly stacked against libc. I just wanted to see what that looked like. So this isn't having a huge effect, but it's having a small effect. This is the definition of eyeballing. Yes. Yes, that is true. Yes. Was I still calling my sign first? Oh, you know what? I was wrong, actually. I got confused because our sign is called sign and it's called libc sign elsewhere. I think we actually were second before. I was wrong when I said we were unfairly going first. Anyway, whatever. We're toggling it now. We're prefetching. We're toggling. This is like better, no matter what, than what we were doing. Could you print the difference? I don't want to. I don't want to. Okay. Because again, we don't want to be like if you're going to be a winner in life, you don't want to be like, oh man, like look, the number is kind of higher sometimes, but sometimes it's like 0.0001 lower, so I kind of win. No, you want to like be decidedly faster. You want to be able to eyeball it and say, yeah, mine is way faster than that other thing. That's how you win. And I don't think we're going to win with this algorithm, right? But I literally don't know anything about this topic, right? It was just the other day, I was like, you know, this math library seems reasonable, so let's just try it. So for me, having picked a random cosine and sine function off the web, having done no real research, we're doing pretty good, honestly. You know? Can make negate branchless now that I'm measuring it. Right. So, okay. You mean this part in the beginning. Right here. Okay, let's do this again. So we're going to go it's x, and then so we do that. And negate equals Flint dot U64 right 63. All right. That seem reasonable to everybody? Discusses implementing the exponential function. I have not seen that. Compute negate before the shift. Yes, thank you, Sean. That would make the code less incorrect. Okay. Sometimes it's good to have people there in chat. All right. Number sign. Oh, geez. You know what we could do? It's like, look, do you want unsigned? Do you want signed? Use whichever one you want. Okay. Whoa, that was wrong. This is a pretty good sign approximation, actually. Right? Okay. Okay, first of all, this is 7FF. Like, don't and you're floating, like, okay. I obviously need more pita chips, guys. Negate is now getting -1. Oh, right. That's a good point. All right. We'll get there eventually. Like if you just randomly change parts of your code, eventually it'll be correct, right? It'll converge on correctness. Okay, negate is still wrong. See? See? Why? So we're right shifting it by 63. I mean, that seems... Oh, that's only if is sign. Right? Okay, see? Look, you just keep making random changes to your code. It's eventually correct. That's how you program, especially if you use the Unity game engine. All right. Don't you love working on the same problem 5 days in a row? This is only the second day in a row, and it was only part of yesterday. Like, but yeah. Wow, guys, look at this. It's neck and neck almost. We're a little slower. For random angles again, right? If we go back to non-random angles, I suspect libc is probably a little faster again. I mean, who knows? libc could be using this same algorithm and they just did exactly what we did and got there, right? I mean, okay. We are a little slower, but like really not that much. We're like, 8% slower. I don't know. We're eyeballing in the extreme. It does look to me like we spike higher, which is weird. I don't understand why we're spiking. I don't know if that's some like thermal downclocking of like floating point operations or something. It does look like we spike higher. I don't get it. Um, when both functions are stable, we're like, 6% slower now or something, which is great. I mean, not in the long term, but this is what Fab's done manually looks like in Clang. What? Wait, I mean Visual Studio. Well, I don't know if I've done this. Maybe it confuses it, but Visual Studio, if you just say fabs of whatever, um, just masks it with, an 8-byte pattern that's off in memory somewhere, right? Actually, yeah, that's what this is. So like, okay, first of all, why are there two of these right next to each other? Because it's like doing two at a time. I don't know. I don't even know what I'm looking at. This looks like a lot of work to me. um, so, so whether this is faster or not, again, we're not looking at assembly right now. Maybe we should, but I'm starting to get tired and I have a call soon. I don't actually know in my head what it's doing here. I guess going float to into float is fast these days, but I don't totally know. I don't know if the compiler is getting confused in a weird way or not. We can get one more little win out of this. We can do the following thing. I'm going to name this underscore Flint for now, just because we have another one below. And I'm going to say here, if it's sine, negate is... Was negate signed? Negate doesn't have to be signed, right? We're going to say there, else, negate, colon equals. So, I mean, the compiler probably optimizes it out, I guess. Maybe not. We're just not assigning it to 0 first, and then we're either assigning it to the result of this or this. I don't know. That probably honestly doesn't matter. Dash O fast gives single and PS. Could store negate pre-shifted in the 63rd bit. Yeah. So it's kind of like the 4-bit thing that we did. We can say negate is the high, because we're going to use it in the high bit anyway, right? So we could change that, change that. This is the problem here, because we need an extra and if we do this, right? So we save this shift, but we have an and here. So it's probably not worth doing. Missed underscore in one of the flints. Oh, yeah. I don't think I like this. I don't think it actually saves us anything, honestly. Because the compiler is just going to see, look, if it's cosine, this doesn't happen. If it's sine, then we just see that this is an assignment, and we just don't bother to do that one, right? So whoops. We could also just declare this once and use it at the bottom again, but Thanks for recommending the Gostak. Yeah, it's a good game. Good game, man. Okay. So I think this is enough tweaking, right? Like, at some point, we just need to do algorithmic changes. This has been a very good progress on this. So let's go back. So we're basically tied. We're a little bit slower on random angles. If I go back and change this to non-random angles, right? So this is what it was before. I mean, that'll go around the circle, 10,000 times or something. I don't know. Wait. 1,000 times. O of 1,000 times. Make sure we didn't break that. Could check what the speedup is from shortening the x minus dp1. Yeah, also, we didn't ever try, like, dropping only the lowest term. Like, I tried scrunching all the constants together, but we could just try using 2. I imagine that if that was good enough, they would have done that. So, all right. So, like, on non-random angles, we are substantially slower still, which is a relatively common use case. Like, hey, I want to draw a circle and, generate, I want to draw like a triangle fan that makes a circle or whatever. That's interesting. Like, I wonder what they're doing. Maybe they have some very weird, like, static state. Except that would be a thread safety problem. But they're like, look, last angle was this, and we got these results for our intermediate variables. And, like, the upper bound of when those are valid is this, right? Like, you can do some very dodgy things if you expect coherency like that. I don't know, though. Could this be due to denormals and stuff? Maybe. Like, maybe we're just checking a little too many things, but those would be well-predicted branches because we're not passing denormals or anything. So it's probably not that expensive. You would expect it's just branch prediction. But, like, why? We're not doing a lot of branches anymore, right? In fact, I mean, there's this one. Okay, that's 100% prediction. This one, that's 100% prediction. This is the only branch, right? Let's just see if this helps at all. Oh, we marked those in line over there. All right. Never mind. See your previous comment. The reduction probably has some extra ifs that specifically handle small reductions. I'm not sure how that would make this faster, but I don't know. Let's try squinching the squinch. Okay. We definitely lose some precision by squinching the squinch. For sure. But let's see what that does for speed. Probably not a lot, but yeah, I mean, it could be that this code, so this code bails on angles of 1,000,000. I don't know what the specification is of the Visual Studio's sine function, right? It might have a much smaller range. We could look that up. I got a Visual Basic. All right. Double sign. $263. Well, loss of significance. I don't know. Anyway. So, I mean, that doesn't seem as hardcore as 1 million. Although at 1 million, we actually reject the input. So that's worse than a loss of significance. um, Are we using 2019? We're using 2017. Good point. I doubt this has changed, but I think we're using 2017, right? What is this? I mean, well, also, actually, okay, guys, I think we are using the newest libc installed on the machine, which probably is the one corresponding to this compiler, but may actually not. Like, I don't know. Like maybe some third-party installs one. Because like this is just for when we compile the compiler, right? But when we're compiling our own programs, look at all these windows we have open. We're compiling our own programs, we link against, we could see, yeah, 2017. Okay. Unless, so that's assuming that it's not like in kernel 32 somehow, but I don't think it is. I think it's actually, all right. Visual Studio 2017. Is it different? I mean, I don't know. Now we're using Chebyshev polynomials. I don't know. This is an algorithm that I just started working on without understanding the base algorithm, which is also not necessarily a thing you should do. But we did make good headway with it. We made it a lot faster. It's using some kind of polynomial approximation. I don't know what kind of polynomial. Oh, did we run our benchmark? Wait. We wanted to see how much faster it was from cutting off that term. The answer is it's a little faster. So it really is, the speed really is down to mostly multiply adds, because we got like 10% faster, and these do like 5, 6, 7. There's like about 10 multiply adds here. You know what I'm saying? So we got about 10% faster by removing one of them. So we need better polynomials. Do you think it is worth writing your own engine if the performance is worse than what you would get from a Unity game? Maybe that's an opportunity to get better at making things faster. Maybe though, performance isn't your number one priority. Maybe your number one priority is having something that does exactly what you want that you can customize. Maybe your priority is expanding your knowledge about 3D rendering. I don't know. You have to answer that. For you, I can't answer that. They're all serially dependent and have to be. Well, I mean, this isn't dependent on what's in here, obviously, right? Not all, but let's see. Like these can fire off all at the same time as this, right? And you meant this one. Yes, I agree with that because the whole point of this is the precision. The precision needs to be maintained. Um, right, and the problem is, of course, all of this is dependent on the value of z, right? Which means it's all waiting on this last guy. And so, like a bunch of this code could move down into here and probably does, right? Because this is all integer and we're not using it for a while. So I would expect that actually, where's our computation of y is? How come I don't see this? So y is up here, right? So as soon as y is computed, we can start doing this. But it's serial, and that's five clocks per multiply. Probably. I don't know what madd is, but when we were looking at multiply and it was 5, it's probably also 5, right? Or 6. Ideally, since it's all branchless, you don't need to manually schedule it. I agree. I'm not suggesting that I copy and paste this down there. I'm just saying the compiler and or the CPU are both working hard to do stuff like that. So I don't need to do it. I'm just understanding what it looks like. Yeah, like modern CPUs do so much out of order that I don't think compilers should really bother to do that much, right? Like to do scheduling. I would just turn off scheduling for the most part. I mean, maybe you do end up helping the CPU a little bit, but I don't know. Might try moving the z calculation up just to see. Let's try it. I don't think it's going to matter. Yeah. Let's make sure we didn't break nothing. Thing is, since it's all branchless, the integer calcs might all still be running, and z doesn't get a chance to run earlier. So you mean like it's not smart enough maybe to say, let's grab that float thing because there's so many, there would be so many integer instructions that you're stalled on one of those and you can't get to the float instructions. Okay. Okay. I dig it. That could be true. What were we at? Were we at 3-4 still? Or were we at 3? I don't remember what we were at. Let me move it back and run again because I honestly don't remember. We were at 3-4? Are you serious? Hold on. And then, of course, see, this is where profiling gets bananas, right? So let's move this back for a second and see if it was better. And in fact, I mean, we can move both of these up, right? And then if that's better, remember, this is the sequential angle case where we were losing. If we go back to random angles and we're really that much faster, we might just win. There was a 1 millisecond diff when you joined. Yeah, I know there was a 1 millisecond diff at some point. I just don't remember if that was before or after we made the initial if statement branch free. It's just we've done so many different profiling steps. Okay. So it's exactly the same. It's exactly the same. It doesn't help us. When is it time to look at the assembly? Not now. I mean, maybe sometime. It's quite possible that there is something really dumb in the assembly that is causing a problem and we could work around it. I don't want to do that now because I have a noontime meeting and I want to have some non-talking before the meeting. So I'm going to end the stream soon. We'll pick the stream back up this evening, maybe. Having a non-libc sign coast this quick with little optimization is a win. I agree. And, you know, we did do the thing where we made the code a bit uglier with the optimization, but the comments hopefully help mitigate that a little bit, right? It's like, look, this was this, now it's this. I don't know. We made it a little bit uglier. I mean, it was really ugly originally, so we made it nice, and then we made it a little bit uglier. So I think it's a net win. Is this a fast sign or general purpose sign? This is a general purpose sign. So if you wanted like fast sign with fewer terms, we could do that. In fact, again, that could be like a compile time argument where you say a prox is a bool, right? And we just drop terms if that's not defined. It's just, I sort of feel like in graphics, we used to want that a lot, like fast approximate inverse square root and fast approximate sine and cosine. And I feel like that kind of stuff has fallen out of favor because back when graphics were not as good, you wouldn't notice small errors, but now they matter a lot, and or they propagate through systems and generate very objectionable problems. And so I feel like people don't really do that stuff that much anymore. I feel like people just do the full precision thing. You just realized we were testing fake sine and seeing the game blow up. The game is using float 8 sine cosine, not float 4. So what we did for our sine is we're just calling float 64 and casting down right now because I just wanted to get something in there. So yeah, the game is calling this one. Like if we wanted a lower precision version, we would either copy paste or have a, I don't know, we probably would copy paste it. But like obviously you don't need as much precision. It would be faster to do floating sine. I don't know how much faster. That's a whole other question. Okay, we're going to comment this out again because we ain't using these. All right, everybody. That's it for today. I think that's all we're going to do on math functions for now because I do want to do a lot more compiler stuff soon, but working on the math library is not anywhere near the highest priority compiler stuff right now. It's just, I did want to make headway on that because it was kind of an open question. Like sometimes on a big project like this, you're just like, there's all these things I don't know the answer to. And one of those was, are we going to have major problems getting rid of our libc dependencies? And I think the answer is no. The answer is we can just do this to all the rest of the functions, which there aren't that many that we're using right now. And then, you know, maybe they'll be like this, a bit slower than the libc ones, but that is fine for now. And, you know, we can research other algorithms. Maybe, okay, maybe I should research other algorithms before doing the rest of those because there might be a more modern library that just uses algorithms that from the beginning are more friendly to modern computers than this one is. Which does not to say, I don't mean like SIMD optimized or whatever. I just mean that whatever computation they're doing is nicer. I don't know. We'll see. I'm not really qualified to research that stuff effectively right now because I've done very little numerical computing, right? But you can always learn, right? You can always expand what you know. So, and I like numerical computing because it all still makes sense. It's generally things are very clear and doing the right thing and not a giant pile of JavaScript garbage, right? So, yeah. So this has been good. This has been good. We answered some questions. And there are more to answer, but we've achieved a reduction in the overall like quantum level of uncertainty around this issue, right? It's one quanta down. I don't mean quantum as in quantum mechanics, but like it's at a lower DEF CON of like how much to worry, or higher DEF CON of how much to worry about this, and that's good. All right, thanks everybody. We'll be back later. Bye.